I'm David Kipping. I'm at the CFA and I'll be starting the Carl Sagan Fellowship in September. I'm interested in extrasolar moons, moons around exoplanets. My bias view, because this is what I'm interested in, would be that exomoons will be playing an increasing role in our study of planetary systems in the future. And if habitable moons are common, then the nearest target for one of these Alpha Centauri-like ships as to find life might be actually a moon that is much closer to us than perhaps a planet.
16 years is a long time. For 16 years I have been searching for and dreaming of exomoons, moons around planets outside of our solar system. But in this year of 2025, there are 0 confirmed exomoons, yet over 5,000 confirmed exoplanets. They have been my Everest, my muse, my morning and my night, a perpetual struggle throughout my career. But my team just used humanity's most powerful telescope to try and finally crack this one. And today, I'm going to tell you what we found. So yes, I've been doing this a long time. In fact, far longer than frankly I ever thought I would. When NASA's Kepler mission launched in March 2009, I was convinced that it would find them. A meter-sized telescope designed to find Earth-sized planets transiting in front of their stars, and so by the same logic, Earth-sized moons should also be detectable too. So I created a project to find them, but after 6 studies and 8 years of trying, the universe just didn't cooperate. It turns out that Earth-sized moons are just not that common. And you might say, well, duh, I mean, the biggest moon in the solar system is 2.5 times smaller than the Earth, but I long hoped that the universe would be far more diverse than our own backyard. But if a 1-meter telescope just isn't big enough, so be it. Maybe we just need to go bigger. Enter the Hubble Space Telescope, HST, a 2.4-meter space telescope. In 2018, my team was able to secure precious HST time to observe one of our favorite Jupiter-sized exoplanets, and remarkably, we found a beautiful, crisp exomoon-like signal in the data. Just look at that dip. But it implied a shockingly large moon, something in between the size of the Earth and Neptune. And not surprisingly, both we and our colleagues had some reservations about whether the signal was real or not, for 2 big reasons. First, no one ever predicted moons could form this big, and some thought it was just too crazy. Now, theorists could explain its existence afterwards, either forming from massive disks or by capturing another planet, but it remained a sticky point for many. The second issue is that Hubble is known to have some subtle and challenging systematic noise sources to deal with, ones that can create fake signals in our data, so maybe the signal was bogus. Now, of course, we did our best to mitigate for these effects, but it remains my greatest concern. What we really needed was another transit of this planet with HST to confirm or deny it either way. And trust me, that's what we tried to do, but when we submitted our request, it was rejected over and over again. The community was so skeptical about this moon candidate that it had become politically impossible to resolve the mystery either way. Now, of course, for me personally, this was extremely frustrating, and I'm sure I will talk about this object Kepler 1625 in another video one day, but for now, it was benched. Hope renewed though when JWST successfully launched on Christmas Day 2021. For now, we had an even bigger telescope in space at last, a whopping 6.5 meters. It collects so much light that our calculations predicted it could detect the transits of moons as small as those around Jupiter and Saturn. I mean, think Ganymede, Callisto, and Titan. This was a big deal. For the first time in human history, we had a telescope that was powerful enough to detect the moons as small as those which we know for sure exist in our solar system. So if we reported the detection of, say, a Ganymede-sized exomoon, no one was going to turn around and say, hey David, a moon that big is impossible. So at least one of the 2 issues with our previous claim seemed to be dissolved. But what about the systematic noise though? Well, when we were proposing to JWST to look for exomoons, this really wasn't that well known. There had been some dedicated efforts to tackle this though, called the Early Release Science Programs, and if you look back at those papers, there were no indications of any kind of major systematic noise effects. Indeed, all the news back then was just how great JWST was doing, performing better than expected. To us, this was more great news, so we used the standard tools to simulate JWST data for a bunch of exoplanets to see which ones were best suited for detecting exomoons. And from that, one gorgeous planet stood out, Kepler 167e. It's actually pure coincidence that this happens to be a planet that I personally discovered back in 2016, but a nice coincidence for sure. What makes it such a plum choice for moon hunters though is that the planet is within 10% the radius of Jupiter and within 1% of its mass. Yet more, it orbits its star every 3 years around a slightly cooler star than the Sun, meaning that the planet should be a very cool 130 Kelvin. That's pretty similar to Jupiter. So this transiting planet was and remains the closest thing to Jupiter we have ever seen, and given the dozens of moons around Jupiter, surely 167e would also have moons too. In our original proposal to NASA, we predicted that if 167e had an exact clone of the Jupiter Moon system, then we should be able to strongly detect the presence of a Ganymede in 84% of random configurations and a Callisto in about half. Unfortunately, Io and Europa are very close to Jupiter, and so our sensitivity is much worse for such moons. Now, the big downside of JWST is that getting telescope time is incredibly competitive. It's oversubscribed by about a factor of 10 to 1. Indeed, our first try was rejected, and I spoke about how devastating that felt at the time. But in hindsight, maybe this wasn't that surprising because 167e's period is so long that it wasn't even observable that time anyway, and so we'd had to pick a less favorable planet. But in cycle 3, everything lined up and we were awarded a whopping 60 hours of data, and recall I told you about how exhilarating that felt too. You know, 60 hours is just a crap ton of JWST data. In fact, it's unprecedented for a transit observation. Many exoplanet proposals are far less, maybe 5 hours or so. But for us, such a huge request was unavoidable because long period planets like 167e take their sweet ass time to transit in front of their star. But I have to say, being given so much data, I did feel a huge weight of responsibility not to screw this up. The observations were taken starting October 27th last year, and we knew that we had 1 year to publish our analysis before the data would go fully public. Indeed, it now is, so feel free to knock yourselves out looking at this data for yourself. To say that I was jazzed about these observations is an understatement. It felt like for 16 years I've been waiting for this moment to arrive, and up to now, time and time again, something had always gone wrong. Kepler wasn't sensitive enough, Hubble had too many systematics, we couldn't secure the telescope time to search, and yet, through all of that, I kept believing it would one day pan out, despite many of my colleagues telling me to give up. But finally, with these observations, it felt like I was getting more than I could possibly have hoped for, and suddenly more than I deserved. I was getting the perfect planet, the perfect telescope. I almost felt a sense of personal destiny manifesting before me. On the day that the data came down to our computers, I asked Daniel Halomi to record us watching it happen. Such was my extreme optimism. My PhD student Ben Cassess here had led the proposal, so together we stared at the screen, hoping. Such moments are always very special to astronomers because no one has ever seen this data before. Who knows what we might see? Yeah, a small moon's probably not going to be visible by eye, but hey, maybe there's a big moon in there. The transit of 167e appeared as a gigantic clear dip in light, so immediately there was relief amongst us that we had at least timed the observations right.
You got it's straight on. We're gonna have a real business. Ben can sleep for the first night in 2 weeks.
But as we stared at it, there was a growing sense of foreboding. Strong systematics were visibly present in the data, spurious noise sources that would go on to occupy my days and my nights in frustration over the coming 12 months. There are several instruments on board JWST, and each one has different observing modes, so we had carefully tailored our instrument configuration to maximize the sensitivity. We used the so-called near-spec instrument in prism mode, which means it collects the entire spectrum of light that the instrument is sensitive to, rather than use a filter as is more typical. But because we collected so much light, we had to use a very short integration time, a bit like the exposure time on your camera. Each data point spanned just 1.6 seconds, and we had over 134,000 of the damn things. But there are limits to how many points you can measure before the detector on board needs to reset, and we hit that limit 5 times. So you can actually see here the reset moments. After each reset, the brightness of the star seems to suddenly increase. Of course, that's not real, that's just an artifact of the detector. Even worse, within each of these 10-hour segments you see here, there's clearly a slow trend downward. Again, that's JWST causing that, that's not the star. A classic technique to deal with systematics like this is to look at one or more other stars in your image and see what they're doing. You can then use these comparison stars to calibrate out your data, and in fact we had done that successfully with the Hubble Space Telescope previously. But unlike Hubble, the field of view here is so tiny that there are no other stars in our images to even compare to. So we're really up the river without a paddle here. Now you might think, okay, fine, no problem, let's just fit a trend through those models. And sure, you can do that. Let's say you try a quadratic trend. So that's a plus b times t plus c times t squared, where t is time and abc are the coefficients of your trend. Well, now we have 6 segments, so straight off the bat, that means there's 18 trend parameters. Our astrophysical model, which describes the planet and the moon, is another 14, so with 32 parameters in total, the software we use to search for exomoons really struggles. The dimensionality is just too high. So for the first 4 months or so of the project, I had to invent basically an entirely new statistical technique to deal with this problem. Okay, fine, no problem. I mean, statistics is my bread and butter, and hey, I've waited 16 years already. What's another 4 months?
Tie both consoles into the Enterprise main computer core, utilizing Neural Scan interface.
There is no such device on file.
No problem. Here's how you build it.
So after that side quest was completed, we were finally able to run our fits on the data. And let me tell you that what we found was genuinely quite shocking. Before I reveal that, we are so grateful to Incogni for supporting the production of this video, a truly outstanding service you need to check out. Staying safe online has never been more important than it is today, because there are AI companies out there that are literally scraping the entire internet, and there are data brokers who are harvesting your data and selling it on beyond your control. And I'm talking private data like your address, telephone number, employment history, medical history, and much more. So that's why I'm so relieved to have Incogni protect me as well as the rest of my family. They hunt down your data and then use the full weight of the law to make sure that it gets deleted. You can see on my dashboard here that over 1,200 data removal requests have been completed thanks to Incogni, saving me nearly 1,000 hours of time. The new custom removals feature is particularly powerful. Just paste in the link to a website where you find your data and Incogni will take care of the rest. So, to fight back, enroll in their protection plan at incogni.com/coolworlds for an exclusive deal of 60% off using my code COOLWORLDS. Look guys, you will not find a better deal online, and there is a 30-day money-back guarantee here. So once again, that's incogni.com/coolworlds and use the code COOLWORLDS. Now back to the video. Okay, so when we ran the fits, it started screaming exomoon at us, and I'm talking big exomoon, about the size of the Earth. When I first saw this, I was both excited and terrified. Excited because we had a signal, and I mean a bloody huge signal, over 12 sigma significance. That's the kind of statistical significance that astronomers fantasize about, but also terrified because it seemed too good to be true, and after all, this wasn't my first rodeo.
All of this is just a little too perfect. Telling us everything we want to hear. They even turned down the beds. The only thing missing was chocolates on the pillows.
It does seem convenient.
So the next step for me in this kind of process is that I want to actually see what the Fitz are doing. Where are they actually placing this exomoon? Plotting it up, you can see that the Fitz had placed the moon right on top of the planet, which, by the way, is so huge it shoots right off the graph. But what's really worrying about this is that location implies a moon which is very close to the planet. I'm talking closer than Io is around Jupiter, an almost atmosphere skimming moon.
I know it's not what you were hoping, but we have sent you all the data we've collected on the Delta Quadrants.
Your intuition was correct.
Unfortunately.
Now, as I'm going to try to explain to you here, after many years of moon hunting, I have learned to be deeply skeptical of these kinds of signals. One reason is that our models normally assume the star is homogeneous, in other words, a plain, boring star. But any weirdness, like a flare or here a star spot, mean that our model of the planetary transit isn't quite right, and so there'd be a tiny deviation left over by our planet model. The moon model sees that deviation is like, hey, no worries guys, I can explain that. So naively it looks like you've just detected an exomoon, but in fact it could just be something slightly off with either your star or planet model. The other headache is that earlier assumption of a quadratic trend. You might rightly say, David, how do you know that that is the right trend? And to that I would say, I don't. No one knows, and that's the problem. Even in the early release science papers, including ground-based testing, they see these trends but simply don't know what to do with them, so everyone just guesses. Yes, literally guesses a linear or quadratic line.
This way.
You don't really know, do you?
What?
I mean, you're acting like you know exactly which way to go, but you're only guessing. Do you do this all the time?
There is no first principles engineering calculation to prove that this function should be a gamma function or an exponential function or something else. We have no bloody idea. It is that terrifying moment in science when you realize that no one knows the answer and everybody's just been making it up as we go along. Now, I am very sensitive to this because the same damn thing happened with Hubble and Kepler 1625. Again, there was a huge debate about the right function to use, and even today, 16 years after the instrument used was installed on Hubble, still no one knows what the right function is. And changing the function matters. With Kepler 1625, it changes the size of the implied moon by a factor of 2. So we did the good scientist thing of trying a bunch of models, linear, quadratic, exponentials, and more, every time we see a big moon, but its properties did vary substantially each time. Finally, we turned to a sophisticated technique called Gaussian processes that you can kind of think of as like a agnostic, highly flexible model. It doesn't assume a specific form, rather it models a memory-like process in the data. On top of this, we tried different ways of processing the raw James Webb data itself. We tried one widely used package called Exotic Jedi, cool name, and then we also wrote our own custom algorithm which was much more conservative in its assumptions to try and maximally suppress the systematic noise. In addition to this custom method, Ben also wrote an entirely new reduction package from scratch, so completely different from custom and Jedi, and this one he calls Katadin. In the end, we presented a grid of 3 different reduction codes, that's Jedi, Custom, and Katadin, and 4 different models, quadratic, exponential, and 2 different Gaussian process approaches. So, 12 different possibilities altogether. Across these 12, 7 of them find strong evidence for a moon, but amongst the 6 Gaussian process models, only 2 of them bear out. So these more sophisticated models seem to largely kill the moon, a possible warning sign. One elegant way of seeing what's going on is to look at the data and ask for each of these fits. Where does it find the strongest evidence for an exomoon? Which part of the data is really driving the story? So here, each colored line is the average signal location across the 4 different trend models, where each color corresponds to 1 reduction pipeline. For comparison, the total average is in black. So they all seem to consistently suggest that the signal is driven by 2 locations, one that occurs right in the middle of the transit of 167E and one just after. But notice how Exotic Jedi goes a bit wild, adding additional signal in other places. Indeed, the moons recovered from Jedi are way bigger than the other models, and when you look at the light curve, you can actually see what's going on here. The trend models weirdly turn upwards in the middle of the transit in order to accommodate a giant moon. From these tests, we realized that the Jedi reduction just wasn't that trustworthy, and so going forward, we relied much more on our own reductions. Let's try averaging across reductions instead, and plotting 1 colored line for each trend model we tried, the same 2 dominant regions appear. But notice how the quadratic and exponential trend models both cause that post-transit signal, whereas the Gaussian processes don't seem to see anything there. The black is the average, remember, so it just dives halfway between these 2 extremes. Thus, because we believe the Gaussian process models are more robust, we think this second signal is likely spurious. That means the only signal all of the methods and reductions can agree upon is this one, the one that occurs right in the middle of 167E's transit. Now remember earlier how I told you that the planet model typically assumes that we have a boring homogeneous stellar surface, but if there was a dark spot on the surface, as the planet passes over it, it would introduce an upwards bump in the light curve. Indeed, we've seen these star spot bumps in countless transit light curves before. Now, you might naively think that there's no way that a planet plus moon model could possibly cause an upwards increase like this, because after all, surely all a transiting moon can do is to block out starlight. But if the planet plus moon pair enter close together, the flux decreases by their combined sum. And then, if the moon eclipses the planet whilst the pair are actually eclipsing the star, then the flux will temporarily increase, since now only the planet is blocking out starlight. This is known as a syzygy event, and it has long been recognized as being highly degenerate with star spot crossings. If you go back to the Kepler observations, 4 years of data shows no clear evidence of spots on this star. But the James Webb data are so much more precise that small spots could have evaded detection by Kepler, yet still appear here. Indeed, we found that such a scenario could plausibly explain this event. Even worse, the spot is likely only a little bit cooler than the stellar photosphere, meaning that across JWST's spectral band, we wouldn't expect to see any obvious chromatic changes. In other words, it would look very moon-like. Now, this doesn't prove that the Wiggle is indeed a star spot. It could still be a very close-in Earth-sized moon, but we have a really good alternative explanation at hand. This is an incredibly dangerous and tempting data set. It would be very easy for me or someone else to push the exomoon narrative upon you. Indeed, maybe someone actually will try to do it in the future, I don't know. But at least for us, it doesn't meet our standards of evidence. There is just too much ambiguity here. And so we leave JWST empty-handed, at least for now when it comes to exomoons. We have a pair of papers that have come out on this. One is about the moons and one is about the ablateness of the planet. That latter question was unfortunately also somewhat stymied by the systematics, but we can at least constrain the ablateness to be less than that of Saturn. Links down below. And we plan to drop a 3rd paper soon on the atmosphere of 167E and possibly even a 4th about the transit of another planet in the system that happens to photobomb our observations, a super Earth in fact. So stay tuned for all of that. But I have to be honest, making this video is not easy for me. I've been deeply moved by many of your supportive comments on our previous videos about this. I know how much many of you are hoping and praying for our success. I really do. And so I can't help but feel like I've let you down. Like I've let everybody down. And for that, I'm really sorry. You know, I was really convinced this would be it. As silly as it sounds, a part of me almost felt like the universe owed me one. That for once, for one damn time, things would work out. And I bet many of you have felt that way, like life is just a series of crushing defeats. And the one time that you think you're going to get a break, the one time that you dare to get your hopes up, is just another goddamn heartbreak. In the aftermath of this disappointment, I've been left wondering what we could have done differently. I've refused to accept that we can't do this. One clear insight is that a single high-precision transit is likely never going to be enough, because any tiny wiggle or anomaly like the apparent star spot crossing is easily explained by a moon model. Too easily. That's its superpower. But every superhero has a kryptonite. Line up a sequence of transits and the moon model's flexibility rapidly diminishes. And by the way, this is true of both this planet and Kepler 1625. To me, this is the clearest lesson from both of these studies. I also want to emphasize that if we do reobserve 167e, we have a chance to do better. Those 6 segments of data were 10 hours each, comparable to the timescale of the transit itself. The fact that they were so coincidental like that is what really screwed us over. But it doesn't have to be this way. We could tweak the instrument settings to avoid this from happening next time around. Now, that would likely come at the expense of some loss in signal to noise, but with 2 transits, that would more than compensate for this loss. And at the same time, it would hugely mitigate this trend problem. Part of me can't help thinking that we should have anticipated this, but neither the JWST instrument simulators nor indeed the literature suggested that this would be such a major headache. Remember that no one had observed such a long transit with the James Webb Space Telescope before, so in our defense, this was really terra incognita.
Again?
Yes. Consider the first time a run-through, a rehearsal to shake out the flaws. The second time will succeed.
So I do believe we can do it, but we have to go back. Now the next transit doesn't happen for another 2 years, so we can't even actually make the request until next year. And perhaps it's asking for 2 miracles in a row for James Webb to give us even more time. But it's also true that the data we have in hand can't be fully exploited without another shot. Maybe 2. The fact is that this planet remains a priori the most likely place that we will find moons amongst the 5,000 plus other transiting planets that we know about. And this planet only transits once every 3 years. If James Webb lasts a decade, that gives us just 3 opportunities to ever observe our best planet. We have to take the shot. We have to try. And you know what? I'd argue that we need more than just this one planet. We need a serious investment of telescope time to investigate at least a handful of prime targets. Exomoons are the next frontier. They are calling to us, whispering in our ear of unimaginable discoveries. The moons of our solar system are already spectacularly diverse. Methane lakes, oceanic worlds, volcanic moons. Just imagine what exomoons might have in store. For me personally, this project has been a roller coaster of highs and lows, but I'm determined to not sit here and wallow and feel sorry for myself for not getting an exomoon. This is not a fairy tale. This is real life. All you can do is look yourself in the mirror, brush yourself off, stand up tall, and move forward. That's all you can do. That's all any of us can do. Just keep moving forward. And who knows, one day it might just work out. So until next time, stay thoughtful and stay curious.
I've always believed that I'm a good enough man to accept the good. I'm a better man to accept the bad. And I believe that.